Kia ora, Year 12 and 13 and Year 11. This is the fourth video looking at some of the Trig skills to get you ready for the internal assessment. So it covers quite a wide range of skills. I'm focusing on the following questions. So this is set 2 and the second half of the questions on that page. And this video is a request from Omer in one of the level 3 calculus classes. So let me know if you've got other questions. I'm going to try and get through all of it, but I'll definitely go through at least the first 2 in this video. I might take a 5th video to do the last one. So let's start with deciding which of these things are going to be identities that we can prove or equations that we can solve. So I'm going to do that before I start writing it all out. Let's just have a quick look at how we can see that. So looking at this top one, we've got a sine of something on this side, right? So we've got a wave, and it's hard to know how to graph that, but it looks like it might be a wave function. It's definitely not a constant. So this one could be an identity. It could be always true. And if you chuck this into your graphing calculator, you'll find that they do match up. The next one has a sine function on one side and a cos function of something of the same thing on the other side. So this is definitely not going to be an identity, right? Because my sine curve is going to go like that, and my cos curve is going to go like that. Oh, that's a very badly drawn cos curve. Okay, don't do yours like that. But you can see that they're not always true, right? We're going to have these points where they cross. I've got some nicer graphs, much nicer graphs of that coming up from GeoGebra. So this one is going to be an equation. And this last one looks a bit funny. So let's quickly have a look at how we know that that's not going to be an identity. Well, let's think about cos of x. So the cosine function goes between -1 and +1. But the cosine squared function can't be negative. So that goes between 0 and 1. And so 6 lots of that are going to be between 0 and 6. So the range for the left hand side is between 0 and 6. Now if we look at the right hand side, we've got sine 2x plus 4. Well, it's not going to be the same thing, because we know that the sine function is between -1 and 1. Then all I have to do here is to say, well, if I add 4, what's my range? Well, the sine of 2x plus 4 will be between 3 and 5. So we can see that the ranges are different. Now you could write it out like that, or you could try and draw the graphs, or just explain that you're going to try and solve the equation and that they don't always match up. Okay, so this one we're hoping will be an always true, and this one they might be sometimes, or they might be never. Right, so now let's look at the first question. This is the graph that I get of sine of 3x. And it's also the graph that I get for 3 sine x minus 4 sine cubed x. So let's start with graphical features. Graphical features of sine 3x are really straightforward. The amplitude is just the usual one. It's 1. The frequency, how many cycles are there in one normal period, is going to be 3 coming from here. And the period of the function is the normal period, 2 pi, divided by 3. Lastly, I've got no horizontal shift and no vertical shift. So that's that one done. Now for the bit that if you're in my A-level class you really, really hate. But let's have a look at the graph that we get from the calculator of the other side. So we'll just draw out a little bit of it, and we'll just put in a few values. So here I've got one of the local minima, -0.523598, and -1. And here I've got the next one, 1.57079, and -1. Up here I've got a local maximum, and it's at 0.523598 and +1. So I can find the period by looking at how long one cycle is. So it's 1.57079 minus negative blah blah blah. So what's that equal to? Well, that gives me, as an ugly decimal, I get 2.0944, and that's roughly equal to 2 pi on 3. So that's the same as the left-hand side. Okay, now let's look at the amplitude. Well, that's very easy to see. The amplitude is 1, and we can see that from these points here. And we can see that there's no vertical shift, and there's no horizontal shift. Now we don't have to check the frequency because we've already checked the period. So what we've got is the two functions are equal. So let's get to the fun part, which is proving that they're equal. I'll just change pen. So we want to prove that sine 3x is equal to 3 sine x minus 4 sine cubed x. We're going to start on the left-hand side with sine 3x. Now, we've got some choices about what to do next, but if you think about our most common things that we use in trig, we've got double angle formulae, right? So sine of 2x, and we've got compound angle formulae. We've got sine of a plus b. So when I see that 3x, I'm not going to use the double angle formula. If it were an even coefficient here, I might go down that path. But here I'm going to say, let's look at how I can use my compound angle formula to break up the 3x. So we get sine of 3x is equal to sine of 2x plus x. Expanding that, we get sine 2x cos x plus cos 2x sine x. Now we can see that we're starting to get somewhere. There are two double angles now in this line. One of them's here, sine 2x, and one of them's here. One of them is a no-brainer for what to do next. Whenever I see sine 2x, I need to replace it with 2 sine x cos x. Okay, it's a really, really useful identity thing. And next, I've got cos of 2x. Now, cos of 2x will often get you out of a hole in a proof, but you have to pick the right version. So this is where you need to go back up to the right-hand side and look at where you're trying to go. You're trying to get blah blah sine x sine cubed x. So you don't want to have any cosine in there. You want to have sine in there. And that's why I'm going to choose this version of the double angle formula to substitute in. Now I just need to clean that up a bit, so we get 2 sine x cos squared x, and I'm going to expand this out, plus sine x minus 2 sine cubed x. So look where we're getting quite close to the end now, but we've still got a cos squared in here. What I really want to have is a sine cubed. The way I get that is using the Pythagoras identity. So we've got 2 sine x times 1 minus sine squared x plus sine x minus 2 sine cubed x, giving me 2 sine x minus 2 sine cubed x, and so on. Finally, I'm going to collect up like terms, and we get 3 sine x minus 4 sine cubed x, which is equal to the right hand side as required. So sine of 3x equals, and we can put an identically equals here now because we've shown that it's always true. And we're just going to write that out. It is always true, right? Just in case anyone missed that we'd said this, and now we're going to say this, right? But we can just go slightly over the top with that. Right, so that's the first question done. Let's go back to the start and see what's next. Right, we're going to do, I'm just going to squeeze in this second one in here. As usual, the video is always slower than I think. So let's look at the graph here. Where is it? Not that one. Not that one. Maybe it is this one. No, it's here. Okay, so this graph shows you sine of 2x plus 5 and cos of 2x plus 5. So let's think about where these are. Well, this is cos of 2 times x plus 5 over 2. So this has got a horizontal shift of negative 2.5. So looking at it, which one's my cosine one? This is my cosine one, I think. And this one is equal to sine of 2 times x plus 5 over 2. So the starting point, the 0 point on cosine, is shifted back to there as well. Right, so blue is sine and orange is cos. So you can see that they do intersect, but they're not the same thing. I'm just going to take that mess off. So we're looking for these points here. Only not exactly these points, right? Because we're told to do values between 0 and 2 pi. Let me just get rid of them. So we're going to do general solutions to solve this, but then we're going to do some particular solutions. So if we've drawn that graph, and we can get the answers for the particulars out of our calculator. Sorry about this, guys. Something weird is happening. I don't know how to use my laptop. There. Right, so we're looking for 4 solutions. So let's get started on it. We've got sine of 2x plus 5 is equal to cos of 2x plus 5. Right, so it's not always true. Both sides are wave functions or sinusoidal. So they'll intersect at some points. If, of course, this actually was an identity, which would be bizarre, and you tried to solve it, you'd end up getting 0 equals 0 on each side. But what you should do is just check before you start whether it's an identity or not. So we're going to divide both sides through by cos of 2x plus 5. So we get sine of that over cos of that is equal to 1. Now that's the same as tan of 2x plus 5 is equal to 1. Now, to work with general solutions, we go alpha is equal to the angle whose tan is 1. And I'm going to make that pi on 4. Right, I'm working in radians here because I need to be, because this thing here's got a 2x plus 5. If you're in my class, we talked about that quite a bit today. So generally work in radians is safer. Unless you're given something like this, sine x plus 60 degrees, in which case you need to be working in degrees. Anyway, that gives me 2x plus 5 is equal to n pi plus alpha pi on 4. 2x is equal to n pi minus 5 plus pi on 4. And now we have x equals n pi on 2 minus 2.5 or 5 on 2 plus pi on 8. Now that's my general solution done. So we know the equation is sometimes true. I've got 1 minute left. So the next bit I'm going to do pretty quickly. Now we're going to put values of 0 in. Values of n in. N equals 0 is too low. So we're looking for values between of x between 0 and 2 pi. N equals 1 is too low. And then we get out the following values using n equals 2 through to 5. We get 1.0343, 2.6051, 4.1759, and 5.7467. Right, nothing very flash about those numbers. I don't mind exactly how much you round them. I wouldn't keep on going to 7 decimal places, it just looks silly. But it's fine as well to chop off. I'd maybe do 3 here. Okay, that's all for now. I'll do another one later.